Yesterday we were talking about the binomial distribution. What does it mean to be binomial? Two possible answers. And what else? So they're independent, so one thing happening doesn't change probability of the other. Anything else? Fixed number of trials. It can't go on forever. We have a set number of times. Okay, and we learned the formula for doing it by hand, and we also saw that we can use the table sometimes, but it has to be of a certain form before we can use the table, because it doesn't have every possible probability and number. And so if it's not on the table, then we have to do it by hand. So let's look at this. 65%. Sorry. 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, what is the following probability? So, why is this binomial? Fixed number, we only have 15 that we're going to look at. There's two possible answers, either they support this or they don't. And they're independent, we're just taking 15 random Americans, not 15 people in the same class or something like that. So find the probability that exactly 10 are in favor. So if we were doing this, my n, the number of people we have is 15. My p, the probability of success in this case, is 0.65. So on part A, exactly 10, that means the x value is 10. So we could do it from the formula, but I said to use your table on this one. So we look at our binomial table. We have to go to the page with an n of 15, the very back page. And our p is 0.65, so cross off until you find 0.65. And then in that chunk of 15, you go down to when your x is 10. B, no more than 6. So what can x be? So 0, 1, 2, 3, 4, 5, 6. So you're going to that, and we are going to add up. The first few you notice say 0, 0, 0, 0 with a plus. That means it is a positive number, but it's so small, the first 4 digits are all 0. And what do you get when you add those up? I got 0.042. Graph the binomial probability distribution with n equals 8 and p equals 0.015. I want to be able to describe the shape of this. I think there were a few on your homework, or at least one maybe, that asked you to draw the graph of a distribution. So my n is the number of individuals that we're looking at. we would have to either calculate all of these probabilities, or if it's one on our table, we could just look at our table. So do we have the n equals 8 and the p of 0.15 on our table? Yes. So lucky for us, we can go there. Right. My x's are going to be my 0 through 8. My y-axis will be our probability. So looks like our probabilities, the highest one is 0.38, so I'm just going to go up to 0.4. I'm going to count by, we have some pretty small ones, don't we? So you could count by whatever. I counted by 0.04s on here to kind of give me a little space. So now we're just plotting our probabilities. So at 0, we had 0.2725. 1 was 0.38. 2 is 0.2376. 3 is 0.0839. 4, 0.0185. 5, 0.0026. 6, 0.0002. 7 and 8 are so small, they're essentially zeros. Okay, so how would you describe the shape of this? If you wanted to you could draw the lines if you wanted, or didn't specify what kind of graph, so you could leave it as just dots. But we can see it peaked way over here, and we trailed off to the right, so that won't be skewed right. I have another one on here, but let's see if we can just look at our probabilities and know. If you look at still with n equals 8, but 0.85. Look at your table. Starts off zeros, 0.0002, 0026, 0.0185. What's that one going to be? Skewed left. Do those numbers look familiar? It's just the opposite, because 1 minus 0.15 is 0.85. So it's just flipped. So this one is skewed left. Okay, so the reason these graphs are important is because the shape can allow us to do some different things. If our data is bell-shaped, we'll be able to find a lot more information about it. And in general, as long as the set is big enough, it will be bell-shaped. So n is the number of people in our sample, p is the probability of success, and then 1 minus p is the probability of failure. If you multiply those, n times p times 1 minus p, then if it's bigger than 10, the shape will turn out to be bell-shaped. Okay, not perfect, approximately. The higher it is, the more bell-shaped it'll be. So with that, if it's bell-shaped, then we can do the empirical rule. And the empirical rule, remember, told us where the data would fall. So if you look back at the front page of your formula sheet, within 1 standard deviation, you should have how much of your data? 68%. Within 2 standard deviations, it was 95%. Okay, so if you're within 2 standard deviations, 95% of the data falls in the middle. That means the probability of being more than that or less than that has to be 2.5%, 2.5% higher, 2.5% lower. So if you're in that window, you would be considered unusual. Right? So if I'm trying to find any unusual data, if it's big enough to be bell-shaped, then we could say if it's more than 2 standard deviations, that would be considered unusual. Okay, so I want you to take a look at this question, read it for a minute, and see if you can figure it out. We are trying to decide if something is unusual. Okay, unusual means the probability is less than what? 5%. So we have to either find the probability of this and check if it's less than 5%, or we can use the empirical rule if it applies. Okay, if I just wanted the probability of this, what is my n? What is my p, the probability of success? Okay, what is my x? So the formula was n choose x times p to the x times 1 minus p to the n minus x. So this would be 400 choose 162, 0.35 to the 162nd power, 1 minus 0.35 or 0.65 to the 400 minus 162. And what happens when you put that? It says overflow. Means it's too much, your calculator can't do it. So, what do? We just shut down our calculator. It won't work. We would have to have better technology in order to get this answer. However, we could check, is this bell-shaped data? So if we look at n times p times 1 minus p. My n is 400 times 0.35 times 0.65. We get 91. That is bigger than 10, so we can say this is bell-shaped data. And if it's bell-shaped, that means the empirical rule has to work, right? So the empirical rule says if you are more than 2 standard deviations from the mean, we'd be unusual. So we need to know the mean and the standard deviations, don't we? How do we find the mean of a binomial distribution? And we get, so mean is 140. Standard deviation is the square root of n times p times 1 minus p. And we get 9.5394. So if I'm wanting 2 standard deviations, we have to add and subtract that twice, right? So I would have to do 140 plus and I want to do it twice for 2 standard deviations. So that means anything above 159.0788 would put you out here in this region that's more than 2 standard deviations. And we could do the less, but I really don't need to because I'm worried about 162. That was higher than our mean. So is 162 past 2 standard deviations? Mm-hmm. Yes. So it's more than 2 standard deviations away. So by the empirical rule, you have to be unusual. And again, the only reason we actually did the empirical rule instead of just finding the probability is because we couldn't. The numbers were just too big. Our calculator doesn't show us enough digits to show us that probability. All right. So I have some review problems. I also wanted to give you guys some time to work. Do you want to work on homework first and review towards the end? Okay, so get some time to work.